Znači, današnje ovako je široka tema. Dobrodošli, dragi gosti, svi se znamo. Posle ovoga znaćemo se još bolje. Kojih stranaca? Misliš na Ljubomira? Okay, let's switch to English. So multithreading, I guess everybody here knows what multithreading is. So this is a rehearsal talk, because I'll begin the same talk in America next week, and you will be like the first people to hear it. Although it's nothing new and nothing revolutionary, just like really common stuff. But I hope you will find it interesting, and yeah, that's why I'm speaking in English. So I guess everybody heard about multithreading. It's like in your CPU, for at least like 15 years now, you have like more than one CPU core in your CPU, 2, 4, 8, 16 now. And the question is how to profit from that additional processing power. So you have these cores, but they're most of the time idle. They don't do anything. And most of the time, like when you're writing your C++ program, your program will be running like in single-threaded mode. Now, when it comes to programming with multithreading, there are several paradigms. Each of them has its own advantages and disadvantages. Like STD thread are really basic. POSIX tracks also in C. They're really basic. They work. You can achieve a lot of stuff with them, but they're complicated to use. And on the other hand, you have like a standard C++ library. You have parallel algorithms in the standard C++ library, like STD parallel 4, and many algorithms nowadays have parallel versions. And OpenMP is somewhere in between. So it's not like the raw threads, but it's not like this standard C++ stuff, which has a disadvantage that you cannot do like something. You can do like this coarse multithreading, but not fine-level multithreading. Now, in this lecture, I'm going to introduce you OpenMP, because it is quite simple programming interface. It's very, very nice, very elegant. You don't have to like do a lot of stuff to achieve parallelization in your programs. So OpenMP is quite old. So the first version is from 1998, and current version 6 is released last year in November. Now, the good thing about OpenMP, so compilers support OpenMP. So all compilers, like MSVC, GCC, CLANG, all the scientific compilers, they support OpenMP. So nowadays, it's not a question of whether OpenMP is supported. Now, it is supported, just depending on version, like 4 or 5 or 6, really depends on the compiler. It's relatively easy to program, and it allows you to parallelize some stuff that you cannot do like with standard library. Now, a small curiosity is that inside the standard C++ library, if you look at the source code, you will see that they implement that stuff using OpenMP, because it's there in the compiler. Okay, so let's go over the basics. So to enable OpenMP, you need to use these compiler flags. So it's fopenmp for GCC and CLANG, or /OpenMP for MSVC. If you don't specify, so the programming interface uses compiler pragma, so you know that sharp, sign, pragma, and so on. And if you don't enable these compiler flags, your program will run like a single, like there are no pragmas, and it will run like a single-threaded program. Yeah. Yes?
So you said that the library is using OpenMP, and if you're using standard library for vectorization and you don't specify a flag, do you get a parallelization or not?
That's a good question, because I don't think you would. Because like if it's in a header and it's not compiled earlier, and you're compiling it, you need to specify fopenmp. And I look at the source code and I saw it there. So I look, it's in the headers, like USR include source parallel blah blah blah. Yeah. Although I am not sure, so I am just telling you what I think. So what's the OpenMP? Oh, here on the right you have an example. So there is this concept called parallel region. And inside the parallel region, this code is executed by several threads. The number is not specified, okay, but there are several, so more than one. And this code here, so you see the pragma-OMP parallel, and this is the parallel region between the braces. And you see this sign, OMP get thread number. So this gets the current thread number. It can be 0, 1, 2, 3, depending how many threads you have. I also included this OMP .h. And this is the possible output for 4 threads. So it will print IM, IM2, 3, IM1, IM0. So what happened is that there was no synchronization in this code. So we didn't put any synchronization, so you get something like this. But you see, there four threads in this case will execute the same line. Now, normally this is not what we want. Like, this is not like the use case. It just tells you what the Pragma MP parallel is. So how do the parallel region works? So at the beginning, you have this. So before the Pragma, everything is executed as single-threaded. Now you enter Pragma, then now you have this fork where 4 threads are being created, or 5 in this case. And then this is executed. This code is executed by each thread. And finally, at the end of the parallel region, all threads synchronize. So this is the join step, and then it continues as single-threaded again. So the question is, this is not what we want. We don't want to print it like this. We want to print it I'm1, I'm0, I'm2, I'm3. So how do we enable synchronization here? So there is another Pragma. So this one is parallel. Now you look at the Pragma OMP critical. So the line or the block after this will be executed like in a mutex. So it's essentially implemented using the mutexes. So there will be one single mutex, and each thread will execute separately. And then you get this output. So this is the Pragma OMP critical. Any questions? Nope. So I get this is quite easy to follow. I don't think it's anything complicated. Now, next question. So you have this loop here. It goes from 0 to n, and C of phi equals A of phi plus B of phi. Now, we want to parallelize it with the knowledge we already have, only with the parallel region. So what do we want to do? We want to take this loop, which goes from 0 to n, and to divide it, let's say we divide it into 4 equal parts if we have 4 threads. Okay. Now, the number of threads, you can get number of threads in a parallel region using OMP get num threads. And you can get the ID of the current thread using OMP get thread number. So there are 2 functions. One gets the total number of threads, let's say 4, and the other one gets the ID of the current one, let's say 0 or 1 or 2 or 3. So each thread gets a chunk which is roughly n of OMP get num threads. So how can we do this? Do you have an idea? Yes. So we have a parallel region before. So this is in a parallel region, but the start and end of this loop depends on the OMP get num threads and OMP get thread number. And okay, so this is an example. Like I try to do it with the all knowledge I have, and this is what I did. So I take the I start. So I calculate the chunk size, which is n. Let's say 1,000. Divided by OMP get number threads. Let's say 4, you get chunk size is 250. You have 1,000 iterations. Each thread gets 250, part of 250. So the start is, let's say, 0 or 250 or 500 and so on. So each of these statements is executed by 4 threads in parallel. And you will get, thread 0 will get I start 0 and I end 250. And thread 1 will get I start 250 and I end 500. Okay? And everybody executes this code. Okay? So this is the idea. How would you do? Do you follow? Okay. Now question is, there are some, if I implement it like this, some things don't work. So what's the problem here? The problem is that when you're using multithreading, in single-threaded programs, in multithreading programs, you have shared variables that are shared among all the threads. And you have a private variable. Each thread gets its own copy. Now, can you guess which variables here are shared and which one are private? Is this chunk size, is it shared or private? Shared. And this I, is it shared or private? It should be private. Private or shared? It should be private. No, it should be private. Yeah, so I didn't specify anything about shared or private here. But yes, I start should be private. I end also, right? What about A, B, and C? Are they shared or private? Should be private, shared, or private? So shared. So all the threads, so A, B, and C are beginning of the point of the blocks of memory. So they're shared all. They're constant actually. They don't change in this region. So we didn't put this. So there is not this. And this code, if you run it, it won't work. And actually, this is like this is how actually you should do it. No, you shouldn't do it like this. You should do it much simpler, but like, let's go over it. This is to show you about shared and private. So shared, there is a concept called shared, and I'm defining N, A, B, and C to be shared. And there is a concept private. I define chunk size, I start, and I end to be private. So each thread gets its own value. And finally, this is called default none. Default none means don't assume some variables are shared or all that is not declared here is shared. Give me a compiler error and I will deal with it. This is very, very good practice to use because if you don't put it, you can get errors that are really difficult to debug because let's say it will assume this variable which is not defined here is shared, but it should be private and so on. Okay, so this is the code actually. Actually, the last thread has this special behavior here. So this because I need to change depending on the size of n and so on. Yeah. Now about this thing, there is this thing. So we have like 1,000 iterations. We have 4 threads. Every thread gets from 0 to 250, from 250 to 500, from 500 to 750, and so on. This is called static scheduling. It's static because we know how the loop will be scheduled before we even start. But this is not necessarily the best approach. Why do you think this is not a good approach? What happens if one thread gets delayed for whatever reason? Yeah. At the end of the parallel region, you remember, you have this synchronization barrier, and everything will be, so if you have 4 blocks, and one takes much longer than the other, then everybody will wait for the longest one. So this is not good, and this is not the best case, the best case, the best way to do it. We statically allocated, statically scheduled this loop here. Now, how it is actually done? Okay. Another thing which is really important is that I specify here private variables like chunk size, I start, and I end. But essentially, I don't have to do it. If you declare it inside the private, they will be automatically private, and you don't have to specify them here. And it's much clearer and much more simple to read. Okay, questions? Okay. So this was, if you had like only pragma-MP parallel, this is how you do it. But OpenMP offers you much more functionality, and you can program much simpler. And yeah.
How do private variables interact with the thread local state? STD thread local.
What I would assume internally, they're just threads. They don't have any. So if you have the thread local variable and you try to, each will get its own copy. That is my assumption. I didn't test it. It would make sense because internally it's all, at the end it's all POSIX. Or on Windows, whatever there is. It's not like, yeah. Now the question is, we had this, okay? And now we introduce OMP4, this pragma MP4. And what happens is this creates a parallel region, and this is our loop. And this pragma MP4 tells the OpenMP runtime, divide this loop over threads. So let's say, it can divide it like previously, from 0 to 250 will be to thread 1, from 250 to 500 will be to thread 1, and so on. But not necessarily. The OpenMP scheduling can divide it differently to avoid that problem that we wait for the slowest thread. And actually, the default is not the static. The default is something called dynamic. The default is the dynamic scheduling of the loops. So this is like really simple. So if you have a for loop, you just put it in a parallel region. You mark what is shared. Ideally, you won't have any privates here because they'll be on inside. And then you have this pragma MP4, and that's it. And actually, you can join the parallel and 4 into pragma OMP parallel 4 and so on. If you compile this with OpenMP enabled, it will work, it will be parallelized. If you decide not to do it, if you want to compile it with OpenMP disabled, it will be just like a loop without any pragmas. Okay?
So is there any requirement on the structure of the for loop, like the counter needs to be standard type?
Yes,
integer,
yes.
And what about the condition?
Yes, yes, yes. Yes. So there are, you cannot put any loop here. Yes?
Those are very small examples. Do they in practice pay off over copying, over cache and such? Does the parallelization pay off in the end for these small examples?
I tested, so I tested all of the examples here. Unfortunately, I didn't bring so it's a complicated question, but I tested all the examples here on 2 machines. And what I saw is that depending on the thread counts, you can control the thread count from the command line. And if you have 2 threads, it will be 2 times faster, but if you have 4 threads, it will be 2.5 times faster. This loop is very memory intensive. It reads A, B, and C from the memory, and it just does 1 operation. So these loops are not typically good, they don't parallelize well. Especially if this loop it's really large and all the data is read from memory. So in that case, everybody's contending for the same memory throughput, and you have this limit there. But some other loops, like if you do a lot of computation, that would be, they can parallelize almost perfectly. Like you use 8 threads, you get 8 times the speed up. Okay? Yeah. So you can control scheduling through environmental flags, or you can control it in the code, but I'm not going to go over that. It's just going too much into details. So if you want to use OpenMP pragmas, your loop needs to be in a, called OpenMP canonical form. So not any loop can be used OpenMP. So it has to be a for loop. So you cannot use it on while or do while loop. Do you know why we cannot use it on while or do while loop? Can you have an idea?
How it would know how to divide over.
Exactly. So it doesn't know how to divide the loop because the while loop can have 20 iterations or 2,000 iterations. You don't know in advance. So that's the reason why the number of iterations of the loop must be calculable before the loop starts. There should be no breaks or returns. If you have a loop with a break, it's called early exit. These loops you cannot use. You cannot use this kind of pragma OMP, but you can use some others. And you can use either this kind of iterator. So you cannot have that the iterator, you increase the iterator, this I inside the loop, only here. And yeah, you need to be able, if you look at the loop, you need to say the number of iterations before you even start. So in this case, it's n. But imagine you are increasing here something and so on. Also here, there's a loop that doesn't, you cannot parallelize it. This one. So this is copy if A of I is greater than value, put it into B of J. So you take the A and then just copy all the values that are bigger than value to B. But you cannot use OpenMP. It won't produce good results. You know why? Yes, J is the problem. So J, you don't know, J, it doesn't develop predictably. Like it can grow in 1 iteration, then stop in another iteration, then grow 3 iterations, then stop 2 iterations, so on. So you cannot use it. It's called loop carry dependencies. Okay.
What happens if we violate the canonical form? I guess we get an error, right?
Yeah, compiler will complain. But for this one, compiler will not complain. I think, I'm not sure. But I would guess the compiler would not complain, you just get bad results. God knows what you will get here. Because this J, whether you define it as private or shared, like if you define it as private or shared, then everything can happen. Questions? Yes? No. Okay, the next thing is called reductions, and here is the example of a reduction. Oh, echo. You have here the sum, which is initialized to 0, and this loop calculates sum of all elements in an array. Now, if you just put pragma MP4, it won't work. So why it won't work? The question is whether sum is shared or private. Should be shared. Peter has a different opinion. Neither. So, okay. Yeah, so if you put it, you can put it share, and then you put pragma-MP critical here. But then your runtime goes from 0.5 seconds to 20 seconds. So that's a bad approach, because you're just putting a mutex here, so it doesn't work. Now the thing is, what you should do actually is you have a copy of sum for each thread, a private sum. And then at the end, when the loop ends, then you take all these private sums, you put them together, you add them together, and you get the public sum. And yeah, this doesn't work, and this does. So I have a parallel region here, and I have private sum here, and then I share this loop with pragma-MP4, so like 4 threads are now executing it, and I'm adding some privates to AI to some private. So I get 4 sums. And at the end, I have this pragma-MP atomic, or pragma-MP critical, doesn't matter, which accumulates private sum to the public sum. And this actually works. This is how it's done. Okay, now the thing here is that the OpenMP offers you like constructs to avoid, it will do this privatization of sum by itself. And this is how it works. So you tell it that you have a shared, and then you have, I'm telling you that this variable sum is a reduction. So what does this mean? Create a private sum, and when you're done with the loop, you will reduce all the private sum to the public using the plus operator. Okay? Questions?
How complex does the reduction can get?
What do you mean? What kind of reductions there are? Here are them. So you have plus, minus. No, I'm not sure there is a minus. This is an error. Multiplication and or, and these other operators. You have min and max. So these are also reductions. So if you have an array and looking for the smallest array, you will use a min reduction. And actually, this is an example of a min reduction. If AFI less than min, min equals AFI, and then you would parallelize it with reduction min on min. So that's the name of the variables. Yes?
So when you use OpenMP like this, is it free to use vectorization or?
The compiler can use vectorization, doesn't have to.
So it's not guaranteed you're going to use like 4 or 5 threads. It might just use 1.
Normally, no. The OpenMP, if you tell it like if you create a pragma OMP region, it will use 4 or let's say 8 threads or 4, whatever. Yeah, it will do. It will do. Even if it lowers performance, it doesn't know that. You're the one in charge. And often, you will see in parallel programming, often you will come into a situation, you think something will speed you up like 4 times, it slows you down by 20 times. That happens all the times. Yeah, that's the problem. The standard C++ library actually has checks, and if this loop is too small, I will just run it on 1 core. Okay. Questions? Okay, next topic is called cancellation points. And this is the loop. So if A of I equals val, then index equals I. I found my index, and I break. Now, what's the problem is this is not OpenMP canonical form. And if you put pragma-MP4, it will not work. So what happens actually? You imagine you're running this on 4 threads. 1 thread finds the solution, it breaks, but it needs to tell all the other threads, I'm done, I found the solution, you need to break too. And this is the cancellation points. It's used to do this. So how does it look like? So I have a parallel region, and then I have this check. This is critical, so it's done. This guy knows better. One, two, three. Perfect. Okay. So this is pragma-OMP critical, so it will set the index. And this pragma-OMP cancel for tells the other threads, cancel this. And here you have, it's called pragma OMP cancellation point. So this cancellation point is where a check is done. So in this place, it will check, did somebody cancel us? Did somebody, all the threads will do it here. And you see it's done in every iteration. So this is pragma OMP cancellation form. Now, for this to work, you need to set environment variable OMP cancellation to 1 or true, I'm not sure. Now, if you check your cancellation points every time in your loop, this lowers performance. And actually, this loop is slower than the loop without single threaded loop. And the reason is because it checks cancellation points in every iteration. Now, how would you fix that?
There are a few iterations.
Exactly. So you check it like every 30 or 60 or 100 iterations. Now, if you do it like that, you won't suffer the performance price of this cancellation check. And here is an example I did it. So I have this section size, and then I have this I goes from 0 to n and increases by section size. And inside I have this minor loop, which goes from I to I end. And then I do the cancellation point. I check them outside of this small loop. So this small loop is 64 plus 16, so 80. 64, yeah, 80 iterations. I check cancellation points every 80 iterations. Questions? This works and is better than the other one. The previous one was slower. I don't have the numbers here, which I'm really sorry. And I will put them, it will make a lot of sense, so you get like a feeling of what you can expect here. Okay, if there are no questions, let's move to the last, another construct, OpenMP. This one is a bit more advanced. So I have here a code called find minimum. It takes a node, which is like a node of a tree, and if it finds the minimum value in a tree. So give it a tree, a node pointer to the root, and it will find the minimum value in that tree. Now, if node left exists, then it goes to the, so this is an error here, find min, and if node right exists, it will go to the right part of the tree, and it will find the minimum value in the whole tree. Now, the question is, can we use multithreading to solve this problem? Now, not the things that we know now, until now, because we need different constructs. Now, the problem with this example is that parallelism is not obvious immediately. So you're at the root. Now, you can do separate searches of the left and the right, okay? And now you can have two threads. Now, you go to the left and right. Now, you can do separate searches on the left and right. So you have 4 threads that you can run in parallel now. And you can, like, the parallelism develops slowly. So you get from 1 to 2 to 4 to 16 threads and so on. So this kind of parallelisms is solved, this kind of multi-threading problems is solved using tasks. And this is the example of tasks. So let me explain what's going on here. So you have this first, you have this like I call it driver function, because it just calls pragma, it creates a parallel region. And inside it, it called find min internal. So this is find min internal. And it does it as pragma OMP single, because we don't want to run four parallel searches. We are just running one search. Now, how do this? So I have here node left, node right. I had minimum left and minimum right. And what I do is I have this contract. It's called pragma OMP task. What happens when you get to here? When you get to here, you're telling the OpenMP, take this code, don't execute it immediately, put it in a scheduling queue. So it doesn't get executed immediately. This thing gets executed, put it in a scheduling queue, gets executed later. And this happens also for the left node and for the right node. So this is the one statement, this is the second statement. Then you have this pragma OMP task wait, which means wait until all the tasks that I spawned here have done. So I have 2 tasks that are spawned, and when they're both done, then this is executed. And I have minimum left, I have minimum right, and this is how I calculate the results. Okay, is this clear? So this is for problems that you have this parallelism that develops slowly, you will use tasks. Yeah, any questions? Yes?
What is first private?
So the question is, what is first private? And the answer is, first private is, when you put private, the value inside will be uninitialized. When you put first private, it will be copied from the output, from the root. Okay, if you just put private, the root will be not initialized, not necessarily. Questions? Okay, I guess this kind of code you would use to, let's say, parallelize quick search. You know the quick search how it goes. So it will take an array, partition it. So it will find a pivot and put all that are smaller on the left side and all that are larger on the right side. And then it will repeat for the left and for the right parts. It will repeat the same process. Now you have two things that can run in parallel: the left side and the right sides, and these are two tasks. And this keeps repeating. Now there is one problem with the tasks, which is not here, which is not obvious here. The problem is when you get to, so you have your huge tree and you're generating tasks. And you have a queue of, let's say, 1,000 tasks. But when you're really low in the tree, so you have a task which is really short, just like one node. And this, when you have parallelization and these tiny tasks, it will be much, much slower. So it won't work. It will be like, this code will be probably slower like 10 times than the original code, and this is not what you want, because the tasks are really small. So parallelization works if it takes like 100 milliseconds to complete, if your task takes 100 milliseconds to complete. If your task takes like 1 microsecond to complete, this task is too short. So you need to stop generating tasks at one point and move on to the serial execution. So here is what I did here. So what I did is, while the depth of the tree, I count the depth of the tree, so 0, 1, 2, 3, 4. And while the depth of the tree is 10, I'm generating parallel tasks. But once it becomes bigger than that, I'm just using the scalar version, so the original version. And this actually is faster, like 2 or 3 times faster than the original version. Okay? So you need to pay attention. So the small task and everything small with parallelization doesn't work. Parallelization requires large chunks of processing. And that's why you don't see parallelization often in your day-to-day codes. You have a small loop, then you have something, then another small loop, then something, then another small loop. There is not a lot of thing to parallelize there. Because a small loop, you cannot split a loop of 100 iterations across 4 cores. Just the overhead of generating threads, synchronizing will kill everything else. Okay, questions? Okay. Okay, so this is the end of the talk in the sense of the OpenMP. Let's do like an exercise. So you have this loop. Can you parallelize it? So this is a code that takes image. Image is uint8. And it calculates histograms. So it counts how many pixels have value 0, how many pixels have value 1 to 255. The question is, can you parallelize this loop? Now, one thing that you can use pragma-OMP critical here. You put like a mutex, but that kills the performance. That's not the way to do it.
Again, we need a private version of histogram for
Yes, that's thing. Yeah, you need the private. So you see, I created the private histograms, and then I'm doing privates. And the end, I have this. This is a reduction step, but you're using private histograms and reducing them to public histograms. That's the catch here. And this is like a few times faster. Okay, yes?
No wait.
So so at the end of this loop, there is an implicit synchronization barrier. When you say no wait, that means there is no. Because this reduction step, you want to do it without waiting for the other threads to complete it. Okay. Let's talk about later. So this is like the most useful stuff you get from OpenMP. So this will cover like 90–95% of your parallelization needs. But some things are just not there. Now, I'll talk about what I didn't cover later. Now, what are the pitfalls of parallelization? Now, the parallelization is like, it's like you see the sun, but it's all per aspera ad astra. You need to go to the stars over needles. The first is that starting and stopping threads takes a lot of time. So when you're executing parallel, when you're entering parallel region, make sure you have enough work there to do. If you don't have enough work, it won't work. And actually, OpenMP has this if clause. So if you run this in an OpenMP, if there is a condition, and in my case, the condition should use parallel if the number of iterations is bigger than 100,000. And the thing is, when you're programming your code, most of your loops will be short. So that limits the applicability of multithreading in programming. It severely limits it. So there is not a lot of things that you can do. Yeah. This thing also applies for tasks. So small tasks, the PragmaMP task, small loops, they just don't work. Then you have this memory subsystem congestion. So you have all these threads, let's say 4 threads, but they're fighting for one resource, and this is the memory or the L3 cache. L3 cache and memory are shared resources, and all CPU share them. And if you have your loop that needs a lot of data from the memory, in that case, the speed up won't be like, if you have 4 threads or 8 threads, the speed will be like 2, 2.5, 3. Like this is also one of the biggest, the things that prevent you from profiting from multithreading. The next thing is you have this synchronization overhead. So if you remember, there is this atomic or critical PragmaMP atomic, which is atomic operation, PragmaMP criticals, which are mutexes. And the problem with this construct is like mutexes are like, again, performance killers. And the solution for that is privatization. We use it in reductions. We use it with histograms. Yeah, every time you can, if you should strive to avoid synchronization and have private copies of your variables just to avoid this thing. Additionally, OpenMP introduces a lot of implicit synchronization. You have, at the end of a for loop, a synchronization. At the end of the parallel region, you have a synchronization. And you can try to improve performance of that by using this no-wait statement, but then you get into other problems. If you didn't do it correctly, it will not work. The next thing is energy and power consumption. So multithreading just uses more power on average. So if you have if you have a single-threaded CPU that does task in 10 seconds, with 4 threads you will take it in 3 seconds, and then single-threaded consumption will be 50 watt seconds, and with 4 threads it will be 64 seconds. And if you know, if you put a parallel and you run it on a computer, you will hear multithreading. You can hear your computer just trying, working like a vacuum cleaner. The next thing is OpenMP works only, well, it doesn't concern us much because all of our architectures, including server, desktop, and so on, are flat memory, so you can access any part of, each CPU can access any part of the memory, but in big scientific computing, you cannot access and not every CPU can access any part of the memory, and then you need to send some messages and so on, and different programming interfaces, different programming APIs are used there. And again, if you have NUMA, anybody know what NUMA is? Okay. NUMA is non-unified memory access systems. So if you have a system, typically server systems that has 2 CPUs, two sockets, will have access. You have local and remote memory, and access to local memory is cheaper than access to remote memory. And you need to be aware of that if you want good performance. And OpenMP allows you to do that with different types of scheduling. You can schedule different, but you need to be extra careful. And finally, one thing that people really often neglect, and this is the topic of the next talk, is that you have bad single-threaded performance. So before you're using multi-threading, you need to make sure you have good single-threaded performance. I forgot to put an example here, so I'll put it. The thing is that there was an example of a code, of a loop, which is like, looks fine. It was some image processing, and it takes like 10 seconds. Then you put it in 4 threads, and it takes 2.5 seconds, and you say, oh, very nice. But then if you fix the single-threaded performance, you go from 10 to 2 seconds. And with multi-threading, you go from 2 to 0.5. So you don't start multi-threading at the beginning. This is like the end step. And this is the motivation for the next talk. Okay, what we didn't cover here. So we didn't cover scheduling methods. So I talked about static, but there are other scheduling methods. We didn't cover sections. So sections allow you, it's like static tests. So it allows you, I want to run this function and this function, 3 functions in parallel. There are some single master constructs, synchronization barrier, and so on. So this thing we didn't cover here because like we don't have time. I hope Peter is awake. Being father is really, really, really exhausting. Okay, so any questions? Yes?
So I want to ask a question about the scheduling methods.
Okay.
You mentioned that the static one is not the default.
No.
Okay, and in this dynamic scheduling method, is it dynamic in terms of number of threads or in terms of scheduling?
No. The
The
number of threads is fixed, like 4 threads, but if you have like a 1,000 iteration loops, it will work something like this. This is how I understood it. Like it will, at the beginning, it will divide like takes chunks of 50, 50, 50, 50, 50, 50, then 25, 25, 25, 25, then 10, 10, 10, 10, then 5, and so the chunks will become smaller as the time progresses when you're coming closer to the end. Yeah, that's the idea of dynamic scheduling. In idea, because if one thread gets delayed, some other thread will pick it up. This is the dynamic scheduling. And there are also other types of scheduling there.
Okay, and one more question, a little less defined maybe. Is there some type of rule of thumb, let's say, how big a loop needs to be, and the number of threads that would be, let's say, optimal to use for a loop of a certain size?
So, like, I wouldn't give any recommendations because it really depends on the system and on the type of loop. There is this metric called arithmetic intensity of the loop. It's a ratio between the number of data bytes of memory and the number of operations on the loop. And there is also number of iterations in the loop. And depending on all these factors, the speed up factor can be bigger or smaller. So the simplest way to do it, try it, code your program, and try changing the number of threads, and try changing the number of threads, and then you will see what's happening. It's really dependent on the system.
Thank you.
Yep. Yes?
Do the reductions support custom types?
Sorry?
Do the reductions support custom types, for example, a type that defines the operator plus?
So I know there are some custom reductions that you can, in the newer versions of OpenMP, you can like define a custom reductions. So not only the built-in ones, but I don't have any more details. I never use them, so I don't know exact details. But OpenMP newer versions allow you to define even on custom types and custom types of reductions.
Okay, so a histogram can also be a reduction.
Yeah, newer version of OpenMP can do histogram reduction without this explicit allocation and so on. Yes? Yep.
Because I'm trying to imagine on the code what you just said, how it will look like.
So it will be like, instead of having this and this, you will have here pragma MP4, a reduction, or maybe outside, maybe in parallel region, pragma MP, parallel reduction reduction hist type is plus, and then you need to specify the size of histogram, something like that. I never use that kind of syntax, so I don't know. But yeah, that's how it's done. Now the question is, I get these are all the questions, right? Do you want to do a break or do you want to continue now? Let's continue, okay? That's my people. So how much time did we need for this one? 40 minutes?
Yeah, something like that.
Mm-hmm. So I was talking about the pitfalls of multi-threading is that you don't have a good single-threaded performance. And in this talk, I'm going to talk, so this is the second part of the talk. It's like a bigger talk which has two parts. And in this part, I'm going to talk about compilers, autovectorization, how you can help it do the autovectorization. So I don't know if everybody's familiar. I'll do a short introduction on vectorization. So in modern CPUs, you have these special vector instructions. So instead of processing let's say one float, and then loading one float, then loading another float, then adding together those two floats to produce one result, you have an instruction that loads 4 floats and from A. So this is our original loop. And this is our vectorized loop. The compiler generates this for you. So it loads 4 from address B plus I, and it loads 4 from address C plus I, and then it performs 4 parallel, so 4 vector additions. Imagine this is B and this is C, and then you add them together, and you get 4 results in the ATMP, and then you store this to the memory. And you see that the loop increases instead of by 1, it increases by 4, because we're processing 4 vector values in a single iteration. Now, these SIMD instructions, they're everywhere now. Like all CPUs since 2001 have them, and you have modern, like this laptop has AVX, and it supports 8 floats. It can process 8 floats or 4 doubles in a single iteration. Now, the compilers are aware of this. So here's how it looks like so this is in memory, and I have vector A and vector B and vector C. So I take 4711 and load them into a vector register, 4711. And then I take 3280, and I load them here, 3280. And I add 4 plus 3 is 7, 7 plus 2 is 9, 1 plus 8 is 9, 1 plus 0 is 1. And then I store these results back to the memory. So ideally, you would get like a 4 times speed improvement compared to the original non-vectorized version. Now, if you have if your system supports SIMD, and most of them now do, like all of them, compiler will take advantage of this. So it will generate like vectorized code. You need to enable optimizations like O3 on GCC or O2 on CLANG, and you need to specify proper architectural flags, MAVX2, or something else, like if you're using Neon, you will need Neon and so on. You can check if the compiler actually vectorized the loop. And there are 2 ways to check. One is to look at the compiler optimization report like this. And the second one is to measure speedup. If the speedup is like 3 times, you're probably using vectorized version. If the speedup there is no speedup, then you're probably using scalar version. Sometimes vectorization either is not possible for one reason or another, or it's not efficient, like it's not faster than using scalar version. And in that case, the compiler will omit vectorization. And we can help the compiler. And in this talk, I'm going to talk about how do we help the compiler. So when it comes to auto-vectorization, there are these called vectorization inhibitors. And these are the things that prevent vectorization. We'll cover some common vectorization inhibitors. Now, you will do these steps before multithreadings. And these techniques will help you even when there is no vectorization. Even if the compiler doesn't vectorize anything, you will get speed up if you apply these techniques, because it just decreases the number of instructions that needs to be done. So what are the vectorization inhibitors? So first one, if the data is not sequentially accessed. So vectorization works best if you have like an array of floats or array of doubles. If you have like a hash map of doubles, linked list of doubles, something like that, you cannot apply vectorization, at least not easily. The compiler won't do it. So the second thing, the loop must not have loop carried dependencies. So loop carried dependencies is when this iteration, the data for this iteration in the loop depends on the previous iteration. So I'll explain about with an example a bit later. Also smaller loops with a really, really small trip count, not like 1,000. Like if you have 3 iterations in the loop and you're processing 4 floats, you cannot vectorize that kind of loop. And also finally, if you have a loop with many conditionals. You have a for loop, and you have if, else, if, then. So these loops also vectorize poorly. Yeah. Any questions? Let's get on to the meat. Okay. So as I said, all architectures, including Intel, Neon, whatever you think, are most efficient when they're accessing data sequentially. So the data should be stored in arrays or vectors. It should be accessed from left to right or from right to left. So no jumping around the array. So that's not sequential access. So here is an example. What happens when the increment in the inner moves, so this is the loop, 2 loops actually nested. I'll call this loop nest. And what happens when the j inside the loop increases by 1? So what happens to these pointers? So we have 3 pointers, out, in, hist, and index. Sorry, 4 pointers. So what happens when j goes from 0 to 1? Access to this I times n plus j. So if it was I plus I times n, it just moves one place. So this is a sequential access. This one, when j increases by 1, instead of we are currently on this value, and then we are skipping over n values. So this is called a strided access. So there is a sequential access, there is a strided access. That's what happens to the index of j. What kind of access is that? Sequential, strided, or something else? No, index of j, not hist of index of j. What kind of? Yeah, read it. Yeah, sequential. Index when j increases by 1, the index increases by 1. And with histogram, this is like indirect access. It's like just random, depending on the value in the index, but it is essentially random. So we have 4 types of accesses, 3 types of accesses here. There is a 4th type. I didn't give it here. Yeah. So one of the techniques. So what about this? Access types? So sequential are the best. Strided are the next worst, and random are like the worst. And essentially, we would like to have more better accesses and fewer bad accesses. So this is the result. So if we have like 2 these nested loops, you can exchange the outer and the inner loop. And I did it here. I put the loop over j outside and loop over I inside. So j is outside and I is inside. Now let's do the analysis again. This time I increases by 1. And when the I increases by 1, this axis becomes strided, I times n. When here increases by 1, this axis becomes a sequential. Index of j becomes constant. It doesn't change at all. So you can just move this, you copy to a temporary variable outside of the loop. And then finally, histogram of index of j, if this is constant, then histogram is also constant, okay? So originally we had sequential, strided, sequential, random, and now we have strided, sequential, constant, constant. And this loop actually is better, has better performance than the original one. Okay, so here an example of matrix multiplication. So I did the interchange of the outer and inner loop here. Now let's do the analysis here. What is the access pattern? Let's do the first one here. What is the access pattern of C of ij in this? Constant, yeah. Because the loop increases, the innermost loop increases by 1. K increases by 1, that means that this is a constant. This is a constant also. And this one here? Yeah, so it's a sequential. And the last one?
Increases by whole row.
Yes, by whole row, yeah. So this is a strided. And what about this one? What is the access pattern of this one? C of ij. Sequential, sequential, this one? No. No. Constant, constant, because there is no j in this expression here. And finally here, sequential. So we have 2 sequential, 3 sequential, and 1 constant. And originally we had sequential, strided, and constant, sequential, strided, and this one has better performance. So this kind of loop interchange typically on a large matrix will make like 3 or 4 times faster, maybe 5. Okay.
So the point of this is for the compiler to pick up
The compiler will probably vectorize this loop, and it won't vectorize this one. So this is what I had in, like, you cannot guarantee it, because there is a way to vectorize even with threaded, but essentially you will get like typically 3, 4, 10 times, depends on the size depends on the system. Now, the compiler could in principle do this for you, but they never do it. I just saw it once. And it wasn't like a standard compiler, it was like some, I don't know, NEC compiler for some kind of scientific system. Or GCC, CLANG, and MSVC, they don't do this, okay?
Sorry, does the improvement come from the local cache access, or because the compiler is...
Both.
Both.
So the one thing is that even without vectorization, this will be like 2 or 3 times faster because it has better data access pattern. But another reason why it's faster is because of the vectorization.
So in vectorization, does the constant access pattern offer an advantage over a sequential one?
Yes, constant vector access pattern, you can keep that value in a register. You don't have to reload it from the memory all the time. Smart compilers can do that. You can actually take this value here, you put it in front of the loop in a float, you store it in a float, and then just use it from a register. Constants are like the best, they have 0 latency because it's in a registry. Okay, questions? No, cool. This was the so with regards to compiler vectorization, this is probably what you had. If you want to improve additional speed, you will need to move to manual vectorization. This is just too much topic for today, so for some other talk. Is a rule of thumb, compilers won't vectorize loop with threaded and random accesses, with some exceptions, but compilers don't do that, you can do that, and whether it will be faster or not, it really depends. But you should think about memory access pattern. This is like the most important things. If you have a bad memory access pattern, your bottleneck is there. Your bottleneck is in the memory access. You can do whatever, but until you fix the memory access pattern, nothing will get better. Okay, so in the previous example, we had loop interchange, and we had like perfectly nested loops. So perfectly nested means there are no statements between the outer and the inner loop. But now I have like this statement here. Now, can we do loop interchange on this one? So what does this loop do? It just goes so you have an image, and it just calculates the sum of average of all the values of all the columns in the image. So this is what the loop does. Now the question is, can you do loop interchange here?
Yeah.
How?
We should loop over the height first, right?
So ideally, if you do the analysis here, this access to image h times width plus w is threaded, and if you do the interchange, it will become sequential. Now the problem with this is you cannot do it because of this float sum and this thing. You cannot do the interchange. What can you please elaborate?
Like add an array.
Where to add an array? Here? Here?
Yeah, maybe add an array outside of the loop and like calculate independently the sum of each row, and then in the end divide.
Yeah. So how you would do it is like you would move these two statements into separate loops, and it will look something like this. So what I did here, I split the original loop into 3 loops, and instead of using sum, I'm using this out of W. And first I'm initializing to 0, then I'm adding to it, and finally I'm dividing it by height. So I didn't introduce any temporary array here, but you can also introduce like some temporary array to do the same. What's the memory access pattern for image? Sequential, yeah. H times width plus W. W is the innermost loop. And what was here? Threaded, yeah. H times width, and H is the outer loop. Okay, questions? No? Yes?
It could be useful, it's not a question, just one for the Americans. It could be useful if you had the benchmarks just
Yes.
to show it's this faster.
Yes,
and then
yes, I
skip
agree.
anything.
But you know, with these things, like it very depends on the size of these images. It really depends on the size of the images. Like the best, if you have like huge images, it will be really much faster. But if you have like tiny images, then it won't be that fast.
So you fake it to have a better presentation.
Yeah, of course. Like everybody does it. Okay, the next thing is then, again, non-sequential memories. So look at this code. It has this struct called foo, and it has 3 members, x, y, z. And then you have this struct called bar, which has 2 instances of foo. Now the question is, what is the memory layout of my bar array? How does it look in memory? So you have, do you have an idea? It's not that difficult. So here it is. So this is the first float, foo0 of x, foo0 of y, foo0 of z. Then foo1 of x, foo1 of y, and foo1 of z. So this is the memory layout. This is how the data is stored in the memory. Now the question is, can this loop be, can you efficiently vectorize this loop? Maybe in this case you could, but like if you have bigger structures or some custom types, then you cannot vectorize that code. So what's the problem here? When you're doing vectorization, you want to do, I want to multiply x by 1, I want to multiply 1 by 5, and I want to divide z by 3, and I want to do these other operations and so on. I want to, so this is not possible vectorization because you can do the same operation. You cannot like, if you have like vector register with 4 lanes, you cannot do one operation on lane 0 and another operation on lane 1. It needs to be either add for everyone or multiply for everyone, so on. So it doesn't work. Vectorization is not possible. What you can do is change the memory layout. You can change the memory layout so all these foo0x are consecutive, then you have another array with foo0y, and then you have a third array with foo0z. And this is called structure of array. So the previous one, this one is called array of struct, and this is like how typically in object-oriented programming you will be storing your data. And struct of array is when you change it, each member becomes its own array. And here is how it looks. So this is the original. And then you have structure of array, and then this is you have this x pointer, which is a pointer to a vector, y and z, and then you have these 2 instances. Now you have, so what's the advantage of this one? So each member is now in a dedicated block of memory, and vectorization is trivial. And when you do this change from this to this, the compiler can do automatic vectorization as well. Yes.
So this is assuming that I want to do some operation that adds all x's,
yes,
or adds all y's, or adds all z's. But if I want to do an operation for, let's say, a dot product or something,
yeah,
I actually want all of them, right? Like I want x and y and z and y.
Yeah, you can load them. Like you are accessing 3 arrays. That is not a problem.
But does struct of array actually in any way benefit me if I want to do some?
So the thing is that with vectorization, vectorization works with simple types, with floats, with double, so on. It's not aware of complex type. Complex type is something, a language invented for you. The hardware doesn't have any idea. It has those floats. And with vectorization, you can do, like, you load 4 floats, and then you can do the same operation on 4 floats. Okay, so let's say I want to multiply this by 2, and I want to add 2 to y. I want to multiply x by 2 and add 2 to y. So in that case, I want to have 4 x's in one register and 4 y's in another register. But the load operations with vectorization, they just load consecutive memories. So if I do vector load here, I will get these 4 data. So 0x, 0y, 0z, and 1x. And I need 4 different operations for each lane. Do you understand?
Yeah.
Okay.
But still, like, maybe if I use struct array and I want to like multiply x by y, for example, x and
yeah,
y
that's not
together.
a problem. You take an x register and you multiply it by y register.
Yeah. Okay. I get it. Yeah.
So instead of doing just 1 by 1, you're doing with 4 x's, you're multiplying with 4 corresponding y's.
Yeah, I get it.
Okay. Yeah, so this is the structure of array. Now the thing that, the other things that really is problem with, not only with vectorization, but generally with general performance is if you have a loop with too many conditionals. So if generally, if you have a loop with too many conditionals, removing conditional, like everything you remove from a hot loop will make that loop faster. And conditional is one of the things that you can actually remove from a loop. Now there are several types of conditionals. Like one is called loop invariant, and they're called loop invariant because they don't change while the loop is running. So you see this function here, it takes a parameter b, and if b is set, it's not a null, then I increase b by 1. Okay, now the question is this b, the value of this b doesn't change while the loop is running, so it's loop invariant, or like I would say loop constant, whatever. You can move this condition outside. How would you move this condition outside, you know? Yep. Two versions of the loop, one where the condition is true and one where the condition is false, and this is how it works out. If the condition is true, I unconditionally add 1. And if condition is false, I just remove the b altogether. The compilers can do this optimization. So they typically do it. It's called loop unswitching. And the compilers do it, but not always. And because the reason why they don't do it, because the size of code explodes by 2, by 4, by 16, depends on the number of conditions. Yeah, so these were the loop invariant conditions. The second type of conditions are called iterator-dependent conditions because they depend only on the iterator. So look at this loop here. It has an I and j, and if I equals j, then do something else, do something else. So this condition here depends only on I and j. It doesn't depend on the data. And this condition is predictable. So if you look at this condition, you know that like if this is a matrix, it will apply only to the diagonal of the matrix. So if I equal j will be on the diagonal, and everywhere else it will be this. And when you know, you can remove this condition. So how would you remove this condition? So there are like few ways of do it. So this is one. Like I set it b of ij to all a of ij, and then just I have special case for the diagonal. Or this is another one to do. It's like I have a loop before the diagonal. It just j goes from 0 to I, and then this is a special case for diagonal, and then I have j goes from I plus 1 to n. So this is like two different ways to do it. So you split the loop into several loops or something like that, and it will make this loop, you have fewer conditions inside. Questions? No? Okay. Also, like if you simplify the loop body, so we have here, in the case of a of I greater than 0, then we add these things, otherwise we multiply them. So whatever you do, you should like move what is common to both outside. And in this particular case, like I have a double C, and if a of I is greater than 0, I load 2, otherwise I load a of I, and then I just multiply it by C. So what's the advantage over this one? Well, there is only one multiplication, and here I had a multiplication and an addition. With vectorization, the problem with vectorization is I didn't put this quite clearly. Like if you have a if or else, you need to execute both the body of the if and the body of the else, and then select between those two. And this is what kills the performance of vectorization. Oh. And yeah. And with this, like, you decrease the number of things you need to do in the loop. Okay, questions?
Yes, we go on the previous slide with the conditional. So, the next one. The last one in the code, yes. So, the conditional on the right, can compiler vectorize that? Can it build some kind of vector and load the values?
Yes, it can. It can load, depending, it will evaluate the condition, and it will load either 2, which is a constant, or of a of I, which is like already loaded. So it will be faster. Now this simplifying loop body is like, you need, I mean, I'm talking about automatic compiler vectorization. while you're doing this and you're interested in vectorization, you should also look at the compiler vectorization report, and you're verifying what the report is saying to you. Is it vectorized now? What is the reason? Why is the compiler reporting it's not vectorized? Unfortunately, I didn't give an example of that because I just thought it would be too much. Yes?
One more. So, like, does the compiler here generate the conditional instructions? Not the ifs with jumps, but
with vectorization?
Yeah.
With vectorization, no. There is a instruction. It's called it's generate. So it loads 4 values of AII, and it compares all 4 of them against 0, and then it generates like a mask, which is set to all when it's where the comparison result is true, so the mask is all 1, and the comparison result is 0, the mask is all 0. And you get this mask, let's say, all 1s, all 0s, all 1s, all 1s. And then depending on this mask, it will load either 2 into another vector register or A of I, and then we'll just multiply A of I by that value.
Okay.
So maybe this is not a good example, because for this example, you would need to actually understand the thing with how the vectorization happens. Because with vectorization, very important thing to know is that vectorization really depends on the way how instructions and how vector instructions work. Okay. Other questions? The next things are loops with low trip count. So trip count is the number of iterations of the loop. So you have a loop with only, let's see, you have the inner loop which has only 3 iterations. Okay, and you're doing something like that. So although this outside of the loop can be huge, because the inner loop is only 3, and you can process, let's say, 8 or 4, now this won't vectorize well. And how do you solve this? Well, you can in this particular case, you can collapse these two, like join them into one loop. It's called loop collapsing. They're just joined into one loop. And this is what you get. So originally you have over I and j, and now you have ij, which goes from 0 to 3 times n. And in this case, this loop can be vectorized efficiently. Okay. Also, you can use loop interchange. We already explained, but one of the applications of loop interchange is if your innermost loop has a low trip count, you can exchange it with the outer loop, which has a higher trip count, to vectorize it. But you need to pay attention. It works only if you don't introduce bad memory access pattern. If you introduce bad memory access pattern, nothing, it's not good. And here is an example here. So here, in this case, this kernel size is like 5. So this loop is really small. And then I use the loop interchange, and I put the outer loop, which is over W, as an inner loop, and then I'm better off. This works better. But this works in this particular example, not generally. So loop interchange is one of the ways. This is actually Gaussian smoothing, horizontal Gaussian smoothing. So if you're familiar with image processing, yes. Any questions? I think you're getting tired. Cool. The final is one of the things that loop carry dependencies. So with the loop carry dependencies, the thing is that you're depending on the previous iteration. So here is an example of prefix sum. And I know that out of I is calculated by using out of I of -1, which is from the previous iteration. Or this one, copy of greater. So I depend on the j, which is calculated in the previous iteration. Both of these loops have loop carry dependencies. And generally speaking, parallelization, any type, so vectorization is a type of parallelization, multithreading is a type of parallelization. And generally speaking, when you have loop carry dependencies, it's difficult to do any kind of parallelization. Of course, there are some tricks. For example, with vectorization, the thing is that you're processing 4 values, but you're going from left to right. With multithreading, you're not necessarily going from left to right. You don't know exactly in which order will the things be processed. So can we do vectorization on loops with loop carry dependencies? Oh boy. This is going to be deleted. Because there was an example how to vectorize it, but it used the intrinsics. I deleted, but I left this thing here. Yeah, loop carry dependencies in general, you cannot vectorize them. You can use something like, here it is. So the way things, if you have an inhibitor inside your loop, whether it is a bad memory access pattern or is it a loop carry dependency, so on, if you split the loop into two loops, one that is vectorizable and the other that is not vectorizable, you can vectorize the vectorizable loop. And here is the loop with the loop carry dependency. So imagine you have this complex calculation here, which is like multiplication, square root, whatever. And then if the result is greater than 0, you're writing them down. So you split them into a vectorizable and non-vectorizable part. This is the vectorizable part. It calculates, it does the complex calculation and stores the result into this temporary variable. And then the non-vectorizable part just goes over this temporary variable and copies to postj++. And this actually works. Yeah, you go over the same data 2 times, but that's not that bad. This actually works. Yeah. Here is an example of loop fission you're using to remove the inefficient memory access pattern. So like this B of index of I is inefficient, but then you do calculate do the complex calculation, and finally you are doing this. Finally you're doing this step, which is non-vectorizable. You're doing it in a separate loop. Okay, questions? Yeah.
Can you go back? Like,
yes.
Isn't it the other way around? Or?
Sorry?
No.
No, it's not.
No,
So
yeah.
this is your inefficient access here. When I increases by 1, this B of I index of I increases randomly, changes randomly. So it's not a good memory access pattern. And this complex calculation would actually make this loop much easier to vectorize. But we cannot do that because of this. And when you split it like this, the compiler will vectorize the first loop. Okay. Further steps. So this is like covers all the vectorization inhibitors. So when you're working with this, you should actually look at the vectorization report and just monitor what goes on and what kind of things it is reporting. Now, one thing that's preventing vectorization, it's called pointer aliasing. So you look at this loop here. So A of I plus equals B of I. And it works fine, like this is perfectly vectorizable, but what happens if you call it like this? A plus 1. So A and B, they alias one another. The 2 pointers are pointing to the same same memory address. And in this case, the compiler must be conservative. So it must generate scalar code here. Even though you know that this never happens, the compiler doesn't, and it must make sure, it should make sure this doesn't happen. So the compiler will omit vectorization when this is useful. And if you're sure there are no pointer aliasing here, you can use a restrict keyword. So you would put double restrict A and double restrict B. And this says the compiler, this pointer is only this pointer is pointing to this memory. Only this pointer is pointing to this memory. And this will be automatically vectorized. But if you call it like this, it won't work. You will get like a bug. Yeah, so this was an advertisement. So when it comes to compiler vectorization automatic, there is a limit to it. So not all loops are vectorizable. Some loops are simply with, for example, this loop copy-if loop, which has loop carry dependencies, can be vectorized. Some loops with low trip counts can be vectorized. Many loops actually can be vectorized with tricks or whatever, but you cannot use compiler automatic vectorization. You need to use vectorization intrinsics. And AVX has one, Neon has one. Yeah, but with vectorization intrinsics, it becomes like this is a training on its own, and I do offer this training. So if you're interested in training, just scan this code. Yeah, so you would need manual vectorization. You would need manual vectorization intrinsic in order to vectorize that kind of loops. And actually, like if you aim to be a performance engineering vectorizations, manual vectorization, at some point you will get to that. Yeah. Let's do some exercise. Yes?
I just want to say that I was one of the courses, and they are great.
This is an example. So we have like an image, and we are coloring image. So odd. So you have two colors, color odd and color even, and we're coloring even. Let's say like blue and odd with red. So with two colors. So and it's like odd, even, odd, even, odd, even. So you're doing like stripes, vertical stripes. Now this is the loop. Okay. Let's do the analysis, memory access pattern analysis. For this j times n plus I, what is the memory access pattern for image? What kind of memory access pattern is it? Yes, it's threaded, yeah. So when the j increases by 1, this increases by n. This whole expression increases by n, so this is not a good memory access pattern. And how would we fix it? We should try loop interchange. It would make a lot of sense. But this thing is preventing our loop interchange. So let's do it together, okay? I hope it connects. Something is like not working here. It's not connecting to like a regular. Oh. Just a second, please. This one. Okay. So this is our code. So this is our code, and we want to do the, so I'll just run it here. You remember this one, right, Milos? Oh, he's not here. So it takes 1.65 seconds, and let's do some optimization on it. So we said that the access pattern for the access pattern for this image is threaded, and let's do the loop interchange. Now this statement is preventing our loop interchange, this one, and I'm going to move it inside, okay? Oh, sorry. Okay, do you see it now? Awesome. Okay, so I'm going to move this. So to do the loop interchange, I need to move this condition inside, okay? Now, what do you think, how much will be the speed up be? From 1.65, what it will be? Sorry?
None.
You,
Because of the condition.
there will be no speed improvements, but we improved the memory access pattern. But we entered the conditions now inside. It used to be outside. So we are doing more things in the loop, but the condition is, we have better memory access pattern. What would you think would happen? Let's see. So it went from 1.49 to 0.34. Okay? So it's like, how much? Like 4 times faster. Okay? So this was the first step. And this is, I don't think the compiler vectorized this. I just think that we just fixing. Now we want to get rid of this. So this condition, what kind of condition is this? Is it constant? Does it depend on an iterator? It can be loop invariant, iterator dependent. Does it change when I change? How would you fix it? Can you remove it? To put it outside of the loop. Just a second. But wait, now, what did I do here? No, I didn't do the loop interchange here. What happened here? So both of them are same, right? What? Sorry, let's do it again. How? Why was it faster if I didn't do anything? Why was it faster if I didn't do it? Yeah, maybe I don't know what happened. But in order to move this condition, like this is I and this is I here, so I cannot just remove it. But I know how this condition changes. If I is even, then it will be color even. If I is odd, it will be color odd. So how can I fix this? Yes? Yes. So I will join two iterations. So increase, instead of increasing by 1, this will increase by 2. And then I have this one. I will get rid of, so I'll repeat this 2 times. Okay? And if this will be color even. Sorry? Oh, sorry. Oh. What happened here? No, it didn't work. It did work. So what's the bug here? Oh, sorry. I know what happened here. So this is another one. And this was the original, right? Oh. And this is the new version, right? So it went from 1.5 to 0.34. So you see buffer same, it's the same values. And now it's 0.03. Yeah, sure. I don't know how to do it. Okay, you see it now? So this is 1.5 to 0.34, and when we remove the condition, it's 0.03. Okay, questions? Yes?
In this last modification, is it the memory access pattern considered strided?
No, it's the sequential. See, it's sequential. You're accessing like the neighboring.
So despite us incrementing I by 2.
Yes, but you're accessing I and then I plus 1.
Okay.
So these are like you're not skipping over anything.
I see.
Yeah.
Thank you.
Questions? Thank you guys for coming. I hope you.